Hi everyone, my name is Alex. I'm an engineer at JetBrains. Today we are going to talk about IntelliJ Platform SDK. IntelliJ Platform is an open source project that provides an extensible platform for building IDEs. JetBrains is the company that created it and during the last 20 years uses it to build multiple free and paid products, mostly IDEs for different languages, that are used by millions of developers. There also are IDEs built by other companies using this platform, an example Android Studio. IntelliJ Platform SDK is a framework that allows to extend and modify any IDE built on top of it through the notion of plugins written in Java or Kotlin. For today's demo, let's say you've already done some research that involves source code analysis and manipulation and built a tool that analyzes the source code and does something useful. For example, finds some bugs or detects code smells. We are going to see how one can easily deploy it inside a popular IDE, showing the analysis results to and interacting with actual developer by extending IntelliJ Platform SDK, thus making results of the research available to millions of real industrial developers. Let's look at two principal scenarios of integrating into IDE. First, and the simplest way, is to only use an IDE UI as a presentation layer to trigger the analysis of the source code by the user and present the results back. The analysis itself can be implemented as an external and independent tool. Even running it as an external process and passing the results back through the standard output is supported. Later we'll see the helpers to do that. Second and more involved way is to work with IDE internal representation of the source code. That enables getting rich structural information about the code, like links to usages, declarations, type hierarchies, and so on, and even manipulating the code in place by suggesting edits and doing refactorings. For this demo, we are going to focus on the first case. Anyways, for both cases, the initial steps for putting your functionality into IDE is the same, by building a plugin using the Platform SDK. A plugin is a simple Gradle build project in Java or Kotlin to produce a jar file plus a plugin XML configuration file, declaring parts of the platform you want to extend. First, how does one go about creating a new plugin? The simplest way to create a new project with IntelliJ Platform SDK is by using this GitHub template. It includes not only the basic build structure, but also good engineering practices like continuous integration using GitHub Actions, release engineering with changelog generation, and a plugin publishing. Another way is by using a built-in new project wizard inside the IDEA. At this point, one has just an empty buildable project that looks like this, but that still can be quite frustrating as the next steps are not always immediately clear. The next thing is to pick up the right integration point for your plugin to extend and customize IDE behavior. There are more than 1,000 extension points defined as part of SDK that allow customization of all aspects of how IDE looks and behaves, for example, an editor or running tests, debugging, language support, and so on. We're going to briefly look only at some of them that cover the first use case, a lightweight integration of an existing tool to help you to choose the right place to call tool from and results result into. These are 4 common places where such integration can be done, and let's look at each of them. Action is a way to add items to IDE menus and toolbars. Users can trigger them manually by name or through binded menu elements or even by a hotkey. This is the simplest and the most general way to allow an IDE user to trigger your tool. It's very simple, you just need to implement these 2 functions. It's up to you though how to present the results back, as it's not attached to the actual editor or code. By the way, here and below all call snippets are just an illustration of the APIs, and the full examples are in the official documentation. Intention actions are in-editor context-specific hints that ask for explicit user interaction over a piece of code. For every piece of code the user is interacting with, all available intentions are determined in the background, and the user may choose to trigger them manually using the bulb icon. You can not only report something on a particular line of code, class, method, or actually any token using intention, but also change this code in place right away. Inspections is the right place for integrating static code analysis tools that run in the background and report the results back in bulk. They're configurable and can be triggered manually by name or automatically as a part of project or language-specific suite. Inspections can also be run from continuous integration using the command line interface in a headless mode that will produce an aggregated report. There are around 5,000 existing inspections built by hands, and there is the whole interesting research direction on whether it is possible to mine more of them automatically from existing changes in the version control systems. Inspection can also provide an automated fix suggestion called Quick Fix, which is shown similar to a regular intention, so a user can choose to apply them immediately. Annotator is the way to provide feedback to the user directly over a piece of code. It is triggered automatically as a part of language parsing pipeline. Helpers exist to delegate implementation to an external process using interface called external annotator. And an example in PyCharm, the standard linter for Python is implemented that way. It may include code modification suggestions through the quick fixes. That as well will be displayed to a user as intentions. We've talked about how to create a new plugin and pick the right place to put a call into your library to do the analysis and then the results back. But we can take it to the next level and integrate even closer by leveraging IDE's rich internal model of the source code. Program Structure Interface, or PSI, is a in-memory representation of a source code. It's a syntactic and semantic model that powers so many of IDE features, such as go-to declaration, find usages, refactorings, code completion, and so on. To see an example of PSI tree from any piece of code, one can either run a built-in PSI viewer by setting this specific property in the configuration file, or just by installing a PSI viewer plugin from the marketplace. Here you can see how it looks like. PSI is an instance of concrete syntax tree, so it includes detailed representation not only of code structure, but also for white spaces, braces, comments, and so on. All the files in a project can be represented by such trees, and one file can combine several different languages. PSI file is the root of structure representation of files' content as a hierarchy of such elements. Every PSI node, for example, representing a file, a class, a field, or a method, implements a base interface called PSI element. PSI Node API allows to extract information that may be useful for your advanced analysis, such as method calls, variable declaration, annotations, and so on. PSI elements are mutable, so you can add, delete, or replace the nodes. Refactorings are implemented as PSI transformations, so you can even run them programmatically as a part of quick fix suggestion. Parsers for building PSI trees exist for all popular languages, so your plugin may have to declare ones that you are interested in as a dependency, and the relevant plugin implementing them will be loaded by the platform at the runtime. PSI is a crucial part of the platform, and you often can see API receiving and passing it along PSI elements. An example, in order to identify a specific piece of code that may be subject to intention or inspection, or analysis. Platform API surface around PSI, including creating, traversing with a visitor pattern, finding elements, is quite large, and digging deeper into it is outside of scope of this short demo. For further reference and details on navigation and manipulation of PSI trees, please refer the official documentation. Last but not least, IDE is an interactive desktop GUI application. So to be a good citizen in this world, the plugin has to respect certain constraints. This is especially important as a common use case when these days a plugin may include an inference from a machine learning model trained on source code. If a latency for operation happens in the UI thread is greater than 100 milliseconds, it is a good idea to put some engineering effort and offload such long-running operation into the background. The plugin size matters. For example, if the machine learning model that becomes distributed as a part of the plugin is 2 gigabytes, it will take a long time to download and install this plugin for a user. Memory consumption is important as well. If for the same machine learning model, inference takes up 6 gigabytes of RAM, users are not going to be happy with the overall IDE performance. Last but not least, IntelliJ IDE is a JVM applications. And there are easy ways to call into native libraries from JVM for interoperability with other tools, but maybe just running a Python script would not be the best integrated strategy into JVM world. So some engineering effort should be expected to integrate your tool into the JVM ecosystem. Thank you for listening. I hope this provides you with some orientation around IntelliJ Platform SDK, a tool to extend popular ideas that should help putting results of the research into the hands of real industrial developers.